Hello everyone, I'm Wildberger. In today's video, we're going to be talking about the geometry of the dihedrons, remarkable, somewhat new approach to the 2x2 matrices that connects strongly with complex numbers and quaternions. We're going to be looking at the geometrical side of this subject and contrasting it with the much more familiar story for quaternions. So we're on the way to understanding complex numbers in a true fashion, having removed any fantasy kind of dependence on real numbers, and we're trying to work over a general field in a much broader vista. And in fact, we also want to gaze towards more general geometries. So it turns out that complex numbers can be created not just in a Euclidean setting, but also in these relativistic settings, blue as opposed to red and green. So there's a combination of things. So we want to understand a little bit the geometry that underpins this very interesting algebra. Okay, so here on this side are quaternions. Very familiar since the days of Hamilton back in the 1850s and so on. Over here, the dihedrons. Much less familiar, and this is a very novel point of view, I think, more or less. Even though ultimately the objects are very familiar, okay, and have been studied hugely, okay, but we're looking at them from a somewhat new perspective. So quaternions, H, things in the form T plus xi, yj plus zk, I, j, and k all satisfy the property that when you square them, you get -1. And I remind you that occasionally we will use this novel notation for minus or negative, putting a bar on top. Okay, here are the other relations satisfied by I and j and k multiplicatively. And if we want to sort of understand a quaternion at large, one of these combinations, one way of doing it is to use this 2x2 representation. So the quaternion txyz can actually be modeled by a 2x2 matrix, however, with complex number entries. Okay, so there's an I here appearing. There's a source of confusion here because these i's here are supposed to represent the usual complex numbers. Okay, so this story already presupposes that we have a complex number system. Anyway, if you have that, then you can represent quaternions in the 2x2 matrix world this way. Now, for dihedrons, the story is much less familiar, but ultimately actually, I think, more fundamental than the quaternions. And it's really worth the effort to understand what's going on here if you are a student of mathematics, especially an undergraduate or a graduate student. Okay, you're going to learn a lot by looking at this situation very carefully. So dihedrons, we're giving them the notation D. A dihedron, on the face of it, looks just like a quaternion, except we'll use D, say. D equals T plus xi plus yj plus zk. And now I, j, and k are new symbols that have the property that I squared is equal to -1 or 1 bar, but j squared and k squared are crucially equal to 1. Here are the relations, products of i's and j's and k's, and they're a lot like the ones over here. So these two are the same, and these two are the same, just the middle ones. The jk and the kj are different. All what you do is you just negate these ones or put bars over it. So over in the quaternion case, j times k is I. Over in the dihedron case, j times k is I bar. And also the corresponding opposite for kj. Now, how do you sort of cook up such a system? Well, beautifully, we can cook up such a system by embedding it in the world of 2x2 matrices over whatever field we're working over. Okay? And the way we do it is we represent this dihedron, which is a kind of abstract thing, by the very explicit 2x2 matrix with entries t plus z, x plus y, x bar plus y, so it's like minus x plus y, and t plus z bar, or t minus z if you prefer. Then the algebra encoded here is sort of automatically captured in the matrix algebra of these 2x2 matrices. That means the various laws of arithmetic, like the associative, commutative, distributive laws, are automatic because they work for 2 by 2 matrices over a field. So we don't have to do a lot of sort of fiddling around to prove that these sort of seemingly curious laws actually support a valid arithmetic. Once we've identified everything inside the 2 by 2 algebra of matrices, then we're basically home free automatically. It's a huge advantage. So note carefully, people, all right? There's a difference here. The dihedrons are directly expressible as 2 by 2 matrices over whatever field you're working with. However, the quaternions, not so. You actually need a prior theory of complex numbers if you want to represent them as 2 by 2 matrices. You can always do it with 4 by 4 matrices without any complex numbers, but that's more complicated. Okay, just a bit of history. So quaternions had been around for a long time, actually in the 1840s, developed not just by Hamilton, but also by Rodriguez. Actually, he wrote a paper on this first. And the multiplication, however, which is perhaps the heart of the matter, how to multiply these things, that actually implicitly goes back to Euler in his work on number theory relating to something called the 4 squares identity. Okay, so we can trace aspects of it back to Euler, but as an algebraic object sort of standing on its own 2 feet, that was Rodriguez and Hamilton in the 1840s. And part of the motivation was to study rotations in 3-dimensional space. Much like complex numbers describe rotations in 2-dimensional space very handily. So Hamilton was looking at an algebraic structure that controls rotations in 3-dimensional space. And originally he was trying to look for a 3-dimensional algebra, but ultimately he realized you had to go to a 4-dimensional algebra to do it. Now, once Hamilton had put these things on the map, further motivations really were in the direction of physics. Okay, in the last part of the 19th century, the major development in physics was Maxwell's theory of electromagnetism. And this theory of quaternions happily allows a nice language to explain and to sort of simplify Maxwell's equations. So that was a key motivator for the subject. However, inside the quaternions, there are these sort of simpler algebraic objects now known as dot products and cross products. So they're kind of, implicit in the story, but they actually go back earlier to Lagrange in the 1770s, who was studying geometry of a tetrahedron. And then after Hamilton and Rodriguez, Grossman was working in this general area, very original work, and then Gibbs and Heaviside came along and sort of elevated the dot and the cross products to maybe an equal or even superior level to the quaternions. So there was quite a lot of tension and debate between the supporters of quaternions and the supporters of dot and cross products. And ultimately, I suppose the vector formulation with dot and cross products gained precedence. And partly because these things can be described purely in a 3-dimensional setting. You don't have to go to this much harder to understand situation of 4 dimensions. But that's not to say that the quaternions haven't played a major role. They have played an important role in other developments, number theory, Lie theory, group theory, lattices associated with polytopes and things like that. So let me explain a little bit further in more detail the connection between the dot products and cross products and the quaternions. So we'll stick with the quaternions at first. So a quaternion Q, t plus xi plus yj plus zk, can be thought in terms of a scalar part, the t, and a vector part, v. So v is then the 3-dimensional vector consisting of the numbers x, y, and z. This has an attractive aspect because then you can describe the laws in a sort of more concise form. The addition is just sort of component-wise, and the multiplication, crucially, is given by the following formulas. That if you want to multiply t1 plus v1 times t2 plus v2, you're going to get a third quaternion, t plus v, where the t part, the scalar part, is obtained by taking t1 times t2 minus the dot product of v1 and v2. So v1 and v2 are vectors in three-dimensional space, and we're talking about what ends up being the familiar dot product. In fact, here it is right here. v1 dot v2, if v1 is x1, y1, z1, and v2 is x2, y2, z2, then the dot product is x1, x2 plus y1, y2 plus z1, z2. That's the familiar Euclidean dot product, or sometimes called inner product. So that's appearing in the formula for t when you multiply these two. And the formula for v, well, it involves a t1 times v2, like you would expect, a v1 times t2, like you would expect, and then some kind of product of v1 and v2. And that's a new product called the cross product or vector product. So v1 cross v2 is the vector whose components are y1 z2 minus z1 y2. That's the first component. The second component is z1 x2 minus x1 z2. And the third component is x1 y2 minus y1 x2. So there's a kind of a cyclic symmetry as you rotate the indices through 1, 2, 3, and then back to 1. Okay, so this is the familiar cross product or vector product in three dimensions. And this is how the quaternion multiplication kind of captures both the dot product and the vector product at the same time. It kind of brings them together. So this is a very familiar story and very important for physicists and engineers, okay? Because these are very important vector operations in three-dimensional space. Okay, now let's cross over to the dihedrons, where it turns out a very similar thing happens, but it is so much less studied. So with the dihedrons, we shift to d equals t plus xi plus yj plus zk. Now these i's, j's, and k's are on the dihedron side. Okay, they're not the same I, j's, and k's over here. The i's and j's and k's satisfying the dihedral relations. And we can do the same thing. We can strip out a scalar part t and call this the vector part v. And then we can multiply two of these guys and we get corresponding formulas. Let's see what they are. t1 plus v1 times t2 plus v2 equals t plus v, where t equals t1 t2 minus v1 dot v2. Oh, that's the same formula as that one. But crucially, the dot product is different. It's not the same dot product. It's a relativistic dot product. The dot product of x1, y1, z1 and x2, y2, z2 is x1 times x2 minus y1, y2 minus z1, z2. So this is a kind of geometry that occurs in Einstein's special theory of relativity. Okay? And it's happening here in the dihedron story. And what about the v part? Well, that's exactly the same as we had there. Okay? t1 v2 plus t2 v1 plus the cross product of v1 and v2. But that crucially is also a little bit different. Here is the dihedral vector product, and you can compare it to here. What's the difference? Well, instead of having y1 z2 minus z1 y2, we have minus y1 z2 plus z1 y2. So we are taking the negative of this first thing. What about the second one? The second one is the same as it was in the Euclidean case. And the third one is the same as it was in the Euclidean case. So to go from the usual Euclidean story to this dihedral dot product cross product situation, let's start with the dot product. The dot product changes in the second and third entries. There are negations occurring there. While the cross product is changing in the first entry. That one is negated when compared to this one. So it turns out that this is part of a general kind of story that my former student, Gennady Noto-Wydygdo, has written a very nice PhD thesis on. And it's all about the general theory of general dot products and cross products in three-dimensional space. and it has all kinds of beautiful applications. So there's actually much more to be said about this, and at some other occasion we'll tell you more about that. Okay, but nevertheless, the dot products and the cross products that are occurring over here, you should think of them as being entirely analogous to these ones, and they satisfy pretty well all the same kinds of relations, maybe just suitably modified with some signs occasionally. Okay, so I want you to think about these two stories as being on something of a par. It's not that the quaternions are vastly more important than the dihedrons. Quite the contrary. Right? They are algebraically on the same level, as you can clearly see. And that means that mathematically we shouldn't be preferencing one over the other. We should have a more balanced point of view. We should be very interested in looking at these dihedrons and extracting rich algebra and geometry from them. And that's exactly what we can do. Now, in order for us to understand the geometry of the dihedrons, it's really good to understand the quaternions first, because it turns out they are simpler geometrically, at least if we look at them over the rational numbers, the more or less standard orientation. So let's start with quaternions. Now, this is a four-dimensional situation, okay, so it is beyond our direct experience. But nevertheless, we can kind of go from analogy, because we can go from 2 dimensions to 3 dimensions and see what happens. And then going from 3 dimensions to 4 dimensions, we can kind of get a sense of what happens. So here is a picture of the 4-dimensional quaternion space. Okay, and it involves the t-axis in this direction and the x, y, and z axes in this sort of 3-dimensional subspace, which is perpendicular to the main t-axis. Right? So instead of having in 3 dimensions an axis like this and a plane perpendicular to it, we have an axis like this and a 3-dimensional space perpendicular to it. And this 3-dimensional space is like our familiar 3-dimensional space, like this one, okay, with an x, y, and z axes. And you'll notice I've kind of drawn them in sort of strange positions with x up here and y here and z here. So this is supposed to be your ordinary standard 3-dimensional space. And actually here we see the unit sphere in that 3-dimensional space with familiar equation x squared plus y squared plus z squared equals 1. Now, when we look in this thing here, we can also look at a sphere. And that's really a good starting point for the geometry, because that sort of pins down a lot of aspects of the geometry, in particular perpendicularity. So the sphere in this 4-dimensional space has equation very parallel to this, except there's one more variable. T squared plus x squared plus y squared plus z squared equals 1. And I'm drawing it loosely as this blue ball here. Okay, but it's actually a 3-dimensional sphere. And inside it, when we slice it like this, we see a 2-dimensional sphere like this. So let me remind you in 3 dimensions what happens. So here is a 2-sphere in 3 dimensions. Okay, let me orient it so the axis is sort of like this. Okay, there's the axis. Okay, now if we take a cross section of this sphere perpendicular to the axis, so imagine a plane, cutting it like this, an equatorial plane, let's say, then the cross section will clearly be a circle. It'll be that equator. And if we move that cross section over to the right or to the left, the slice that it makes is still a circle, but the size of the circle diminishes as we move closer to this end point here. When we get to that end point, then the cross section consists of just a point. And then if we move the slicing plane over beyond that, then there's no more intersection. So one way of visualizing this 2-sphere, if you were a 2-dimensional creature, would be to think of a bunch of slices, each 2-dimensional, that you could look at, and that would consist of a bunch of circles getting bigger up to the maximum there, and then getting smaller, and eventually just getting to a point down there. So a corresponding kind of thing is happening in this 3-dimensional sphere situation in this 4-dimensional space. So what you're supposed to be looking at here is this slice, which is now a 3-dimensional space. Its equation is t equals 0, so it's actually a hyperplane in this 4-dimensional space. And inside it, you have these three axes, x, y, and z. And inside it, you also see the intersection with the big sphere, which is this red sphere that you're seeing there, which is just basically the same thing as the standard two-dimensional sphere in three-dimensional space. Now, to prepare ourselves to go to the dihedrons, we need to first learn a little bit of relativistic geometry. So this is a variant on the familiar Euclidean story, where we start with a relativistic quadratic form. So if we have a vector v, then we define v dot v to be x squared plus y squared minus z squared, instead of the familiar x squared plus y squared plus z squared. This is a relativistic quadratic form which has its origins essentially in Einstein's special theory of relativity, and this geometrical representation of it was promoted by Hermann Minkowski. Okay, and it's a very important aspect of modern physics, so much so that, you know, maybe in the context of 20th century physics, we now appreciate that the global geometry of the world really is more relativistic than it is Euclidean. We happen to think things are Euclidean because we're relatively small in the scheme of things and because we move relatively slowly. So relativistic effects are not so visible to us. But sort of on a larger scale, relativistic effects are much more important. And it's this kind of geometry that actually plays a central role in understanding modern physics. So modern mathematics, is aware of this, but maybe because we haven't spent so much time and effort, enlarging our understanding of geometry in the 20th century, maybe our contact with this is not as deep as it maybe should be. Okay, but anyway, we can think about it. So let's have a look at the consequences of thinking about this as the quadratic form. That means that if you have some vectors, think of all the vectors emanating from the origin, you can still describe them in terms of analogs of spheres. So here, for example, is the surface of the vectors whose quadrants is 1. In other words, that satisfy the equation x squared plus y squared minus z squared equals 1. So that's a hyperboloid of one sheet. It's all one thing. It's what you get when you take a hyperbola, like this one here in, say, the YZ plane, and rotate it, say, around the Z axis. You get a hyperboloid of revolution, like this. Okay. It's actually a very interesting surface. It's actually a rule surface. It has two families of rulings. So one way of getting such things, you take a circle here in a plane and take another circle here in a plane, and you join one point there with another point below it. Not just directly below it, but over adjust it somewhere. And then you just rotate the whole story around. You rotate that thing around. You get a surface that's ruled by those lines. In fact, there's a corresponding second ruling going in the opposite direction. Very important in architecture, for example. Now, we can also, in this case, consider the vectors whose quadrants is 0. Now, in the Euclidean case, at least over the rational numbers, the only point or only vector which has quadrant 0 is the 0 vector. But over here, it's much more interesting. We actually have a cone, as you can see in red, which is the cone of vectors of quadrant 0. In other words, that satisfy the equation x squared plus y squared minus z squared equals 0. So a physicist might say that's the null cone. So it corresponds to trajectories of photons. So it has a very important kind of physical meaning. And geometrically, it's rather simple. It's just what you get. You rotate a line through a fixed point so that the one of the endpoints here goes through a circle. All right? Actually, it should be probably bigger like that. That's a cone. That's the null cone. And then we can also consider vectors whose quadrants is negative. For example, -1. Then what we get is another hyperboloid of revolution called a hyperboloid of two sheets. And that's represented by this green surface there and the second branch of it down here. So you take this hyperbola opening up here, and you rotate it around the z-axis. So again, you get a hyperbolic like cup. So these are different kinds of surfaces that are just determined by this quadratic form. In the Euclidean case, if you look at x squared plus y squared plus z squared equals something, you always get the same thing. You either get a sphere of some radius or quadrants, or you get the point, which is the origin. Okay? In this relativistic setting, you get a wider family. But, and a very important part, remember that I'm trying to encourage you to think more broadly, that we shouldn't just be thinking about geometry over a fixed field, say the rational numbers or the real numbers. We should rather be trying to understand the situation for a general field. So when you go to a general field, then you can get either this kind of story or the other kind of story, depending on the number theoretical properties of the field. So in fact, if we wanted to have a very general kind of understanding, we necessarily must understand this kind of situation just as much as we do the more usual Euclidean story. Okay, so now I can give you a cursory kind of initial orientation to the geometry of the dihedron algebra, which is four-dimensional. And it's very challenging to portray it adequately on a two-dimensional surface. So what I'm going to do is I'm going to show you slices of it, sort of like I did for the quaternions. And we're going to start with the t-axis. So this is the axis actually through the identity, the 1. Okay. So there's the t-axis, and corresponding to a couple of different values, I'm going to show you a three-dimensional cross-sectional slice. So the dihedrons is four-dimensional algebra. If, say, we set t equal to 0, then there's a cross-sectional slice, which is a three-dimensional space. Okay? And then we can draw the usual kind of picture for this three-dimensional space. In this three-dimensional space, there was an x-axis, a y-axis, and a z-axis corresponding to I, j, and k. Okay? In fact, I will be, in this case, right up here. Okay? And if we're interested, say, in trying to understand the sphere, so the sphere would be t squared plus x squared minus y squared minus z squared equals 1. This is the three-dimensional sphere in this kind of dihedral geometry. But it's not the same kind of Euclidean sphere that we're used to. And in mathematics, this usually has the name of SL2. Okay, so it's a very important mathematical object, sort of the heart of a lot of number theory and representation theory. It's something that I've studied for quite a long time in various contexts. So this is another way of looking at it, sort of kind of a geometrical way of trying to represent what this thing looks like. And it is a little bit subtle. So what we do is we first slice it right down the middle. So there's the axis, something like this, okay, but it doesn't look like this. But we're slicing it like this, just like we did for the three-sphere. But instead of getting a cross-section, which is a two-dimensional sphere, we get a cross-section which is a hyperboloid of two sheets. Why is that? Well, it's because we're setting t equal to 0. So if you take this equation, you set t equal to 0, you get the equation x squared minus y squared minus z squared equals 1. And I've got x going up here, okay? That's the x direction. Y and z are sort of horizontal. So if x is equal to 0, for example, then you get minus y squared minus z squared equals 1. That doesn't have any solutions. That's telling you that if you slice this thing with a plane through the origin, which is in the yz direction, it doesn't meet the surface. Okay. So this is a hyperboloid of two sheets. It's the cross-section of the big sphere at t equals 0. If we move up a little bit to t equals 1 and look at that particular cross-section, so that's sort of analogous to like, moving over here until we get to the endpoint. When we did the endpoint there, we just got a single point. Because that was the equation x squared plus y squared plus z squared equals 0. Well, here what we get is x squared minus y squared minus z squared equals 0. And that's more interesting. That's the relativistic cone, the null cone of the physicists, which we showed last time in red. It looks like this. And if you go further, let's say you go over to t equals 2, in the Euclidean case, if you go beyond then you don't slice anything, you get nothing. It doesn't meet the traditional sphere. But over here, that's not the case. If you set t equal to 2, then you get the equation x squared plus y squared minus z squared equals minus 3. And that turns out to be a hyperboloid of one sheet. That's the rule surface. So we have this sort of gradation of things. If you have a slice way over here somewhere, you're going to get one of these hyperboloids. And if you go further in that direction, the hyperboloids are going to get bigger. And then as you move towards here, you're slicing this thing here. Once you get to this thing here, these hyperboloids scrunch down and give you the cone. And then immediately afterwards, they kind of break up into these two hyperboloids of one sheet, all the way from here over to here. And this is where they reach their maximum sort of separation from the origin. After that, they contract back again and move back to closer to the relativistic cone, which we arrive at -1. And then if we keep on going, taking cross sections, then over here we get a mirror image of what we did there. So the whole thing is kind of symmetrical. Is it complicated? Yes. Is it beautiful? Yes. Is it important? Very much so. So this is a fundamental mathematical object. Okay, it plays a huge role in lots of things, and it elevates the importance of relativistic geometry, connects with physics, but it also contains the complex numbers and their important relativistic variants all together. So actually, this story is probably richer and, well, at least as rich as the Quaternion story. And if we're looking to have a broad picture of things, we really want to understand these dihedrons. So let's close our circle here and see how the geometry of the dihedrons connects with what we're actually interested in, explaining complex numbers and the right way of thinking about them in a very general sense. So I'm going to stick with the story over the rational numbers, but let's just keep in mind that we're actually interested in understanding this for a general field. Nevertheless, this is a good orientation. And let me remind you, we're talking about dihedrons. Dihedrons are these four-dimensional objects consisting of these I, j's, and k's. And we can actually make all the mystery vanish just by saying we're just talking about 2x2 matrices over the field. So there's nothing mysterious about I, j, and k at all. They're just 2x2 matrices over a field. Okay, and so this dihedron is just this matrix, and that's all. Okay, and the arithmetical operations are just the matrix operations. Okay, and then of interest is the sphere where the standard quadratic form is equal to, say, 1. T squared plus x squared minus y squared minus z squared equals 1. And now I want to look at this sphere from a different point of view by taking some two-dimensional slices. Not three-dimensional slices, two-dimensional slices. So let's look at just the part of it that consists of t's and x's. So over here, if we set y and z equal to 0, that's like two conditions, setting y equals 0 and z equals 0. It means we're cutting down to a two-dimensional subspace of this four-dimensional thing. Okay, so y and z are 0. We're getting matrices of the form t, x, x bar, t. So we're getting the familiar complex numbers in 2x2 matrix form, which is very natural and very elegant, because then most of the properties of the complex numbers immediately are derived from bigger and better properties of matrices. Okay, and we don't have to do a lot of separate work in establishing all these things. It's just immediate consequences of matrix things. In particular, this quadratic form is just the determinant. Okay, it's the most natural thing in the world. And here is the story of what happens when we restrict to y and z equals 0. Then the equation is t squared plus x squared equals 1. We get our usual unit circle, which looks like a Euclidean circle. And that's the usual complex numbers that we're more or less familiar with, at least done sensibly. That is where we're looking at an underlying field of the rational numbers and not playing games with infinite nonsense. Okay. And notably in this story, the only object which is not invertible, in other words, for which this determinant is actually a 0, is the origin here. So that's the only element in this algebra which is not invertible. And we usually make a big deal out of that and say, that means that this is a field, it's something special. But that's probably not really such a good idea. Yes, it's special, yes, it's interesting, but it's not really capturing the main thing that's going on here, okay? And that becomes clear when we look at the relativistic versions. Over here, we look at another plane where we set x and z equal to 0. This is another two-dimensional plane. Should put the identity in there. There's the identity also there. Okay, so it's a two-dimensional subspace, actually a subalgebra, containing the identity, and its equation then is t squared minus y squared equals 1, which we recognize in the usual t and y coordinates as hyperbola. So this is then the circle in this complex number algebra. Okay, so this is a variant where we're considering matrices of the form t, y, y, t instead of t, x, x bar t. And it's a nice algebra. It's got an involution. It's got a quadratic form. There's the unit circle. But crucially, what it also has, it has more non-invertible elements. So the non-invertible elements include not just the origin, but also these asymptotes of the hyperbola. So that is an important point of distinction between this subalgebra and this subalgebra. And then the green one, okay, is very similar. When we set x and y equal to 0, then we get two-dimensional slice in the t and z directions. The equation then of this sphere is t squared minus z squared equals 1. Has the same form geometrically, but as matrices, we're looking at something different. They're just diagonal matrices with zeros off the diagonal. So we get blue complex numbers, we get red complex numbers, we get green complex numbers, all as different two-dimensional slices. So this is a very poor analog, right? But if this is the identity element here, we're taking two-dimensional slices that go through the identity and also in some other direction. But we're not, in the Euclidean case, we're in this dihedral case where this sphere goes on in lots of directions, and it's a much richer story, and it captures at the same time all three of these very important complex numbers. Great, so we've gone through a lot of material today, admittedly in a rather fast way. There's much more to be said about all of these things, and perhaps a lot of you might like to investigate more deeply why some of the things I've been saying are true and check some of the things. In our next video, we want to close the discussion by looking at the algebraic side of the true complex numbers, now with this bigger picture in mind and being aware that probably the algebra and the geometry have natural and important connections. Hope you'll join me for that. I'm Wildberger. Thanks for listening.